Hello everyone. So in the previous lectures, we had talked about the plane stress and the plane strain conditions, and at the end of it all, we had shown, if we just refer back to the previous page, that when we do not have body forces, or when the conservative body forces are such that the scalar potential V satisfies this Laplacian of the scalar potential equal to 0, then we must have this equation, this biharmonic equation involving the eddy stress function phi, and let us remind ourselves once again that this biharmonic equation includes within it the information from the compatibility equations, the constitutive law, as well as the stress equilibrium equations. So with this, let us go forth and try to look at some possible solutions of this biharmonic equation. Now, operationally, what is done is to look for solutions or particular solution forms to this biharmonic equation. Okay, so we have this equation, and we'll first of all consider this biharmonic equation in the rectangular Cartesian coordinate system only. Please note that all this while we have actually been deriving everything in the rectangular Cartesian coordinate system, because if you look back at all our considerations involving this plane strain, this was all plane strain, and if you go back further, all this was plane stress. So in all these previous lectures, we had been actually talking within the scope of rectangular Cartesian coordinate system only. However, the equation that we are finally arriving at, that is so this equation, this biharmonic equation, is true irrespective of the coordinate system of choice. What I mean to say is that even though it is derived using, as you have seen, the rectangular Cartesian coordinate system, the xy coordinate system, that is, but it is this particular form, this compact form involving the biharmonic operator, it is very much true even if we go to the polar coordinate system, for example. Okay, so but now we'll be only interested in the rectangular Cartesian coordinate system. So what we are basically looking at here is this equation: del 4 phi del x4 plus twice del 4 phi del x squared del y squared plus del 4 phi del y4 equal to 0. Okay. All right. So now the one of the most common solution forms for that is assumed to satisfy this biharmonic equation is the polynomial form. Okay, so we're interested in this polynomial solutions. So the form that is actually assumed is this. Okay, written in a very general sense, it is written like this. Okay, so where m and n are just integers, okay, starting from 0, they may go up to as much as you like. Okay, so both m and n start out from 0. It can be 0, 1, 2, 3, 4, whatever. Okay, and we require that this particular form will satisfy this equation. Okay, now if we just expand it out a little bit, okay, so we'll see that when we set m equal to 0 and n equal to 0, we just have this constant term. Next, if we take m equal to 1 and n equal to 0, we'll have a 1, 0 x. If we take m equal to 0, n equal to 1, we'll have a 0, 1 y. And if we take m equal to 1, n equal to 1, we'll have this first quadratic term, a 1, 1 xy. And similarly, you can understand that we'll have other terms of this sort. Okay, we can keep on writing them out as much as we please. So dot dot dot. Okay, now think for a moment that this phi is basically used to generate the stresses. Okay, so because again we remind ourselves that because we have our stresses in this form, that sigma xx is equal to del square phi del y square, sigma yy is equal to del square phi del x square, and sigma xy is equal to minus del square phi del x del y. Okay, so if we take terms like this, if we take a term like this, you see that all the stresses are zero. In fact, if you take this term also, then also all the stresses are zero. If you take this term also, all the stresses are zero. Okay, so whenever we have, uh, so please note here that let's write down one of the first important points, that terms with m plus n less than equal to 1, uh, they do not contribute to the stresses. And because they are trivially giving us zero stresses, okay, they do not contribute to the stresses. Okay, so it's pointless to take them. Okay, they are always going to give us trivial cases, that the stresses are always zero. Okay, not very interesting. Next, suppose we take the terms which do give us some kind of a non-zero stress field. So the first of those will be terms will be a polynomial form which involve the second degree terms. Okay, so the second degree terms will produce a linear stress field. What do we mean by that? Okay, so we have already crossed out these things. Okay, these are not very useful. So suppose we take terms containing the second degrees. Okay, so this one is a second degree term, this is a second degree term, this is a second degree term. So if we take these things, okay, we have no other terms which are second degree here. So if we take these, so let's say our phi is equal to a11 xy plus a 20 x square plus a 02 y square. Okay, then the sigma xx, that is we can write this down directly, sigma xx is equal to del square phi del y square. So we'll have the contribution from this, we'll have this as twice a 02. Okay, the y vanishes. Next we'll have sigma yy is equal to so that's del square phi del x square, so we'll have that as twice a 20, and sigma xy, that will be minus of del square phi del x del y. Because we do not have any contribution from y here and no contribution from x here, so these will not contribute, but this one will. So this is going to be minus a11. Now see, this is very interesting. A second, so these second degree terms, these are producing so I shouldn't actually be writing this as a linear stress field, that's wrong. Okay, let me make this correction. The second degree terms will produce a constant stress field. Okay, this is very important. Please note down this correction. So when we have the second degree terms, the stresses are all constant. Okay, all the three components of stresses, These are constants, and what this means is that uh, it is basically producing a combination of either uniform tension or compression in two perpendicular directions together with some kind of constant shear. Okay, so perhaps it will look something like this, that we take a rectangular domain like this, where you note that this one can be our x-axis itself, and this can be our y-axis. Okay, uh, so this kind of a stress field uh, will be produced when you have a uniform tension like this along the x direction. It could also be uniform compression. It just depends on what is the sign of this A02. We could have for this sigma yy, we could have this sort of uniform tension or equivalently uniform compression in the y direction. Let me write that clearly. This is our y direction, this is our x direction. Or at the same time we could have uh, uniform shear. Okay, so that also is very much possible. So suppose okay, so that denotes uniform shear. So also here, that is very much possible. So uh, because I have no space left here, I'll just stutter this figure a little bit. Okay, so that represents some kind of uniform shear also. Next, suppose we uh, go on to uh, take the third degree terms, then what happens? So these third degree terms, this is what is going to produce a linear stress field. So what I mean here is that phi can be of the form a 30 x cube plus a 21 x square y plus a 12 x y square plus a 03 y cube. So all four of these terms, they are cubic. So the sigma xx, you please note, uh, since this is del square phi del y square, so only this term and this term are going to contribute, and that will be uh, 2a12 x plus 6a03 y. Next, for sigma yy, will have del square phi del x square, which means that I will have a contribution from this first term, the term involving the a30. I'll get a 6a30x out of it, and from this term, which will be twice a21x. And finally, for my sigma xy, so here I will have a contribution only from these terms involving the A21 and the A12, and this one will be minus twice A21 x minus twice A12 y. All right. So this looks fairly complicated if you want to physically interpret it. So as a simple special case of it, what we'll consider is, suppose we take, okay, so consider the simple special case where we have A12 is equal to A21 is equal to A30 is equal to 0. You set this. Then what we'll have is sigma xx is equal to 6a03y, sigma yy going to be equal to 0, and sigma xy is also going to be equal to 0. So basically this sigma xx here is just linearly dependent on y, and you try to think from where in your studies you have come across such a stress field. Okay, so let me just point out here that if you take uh, if you consider a beam like this which is under pure bending, then from our undergraduate studies we know that the stress field here does indeed have this kind of a linear distribution. Okay, so we have this kind of a linear distribution. So also on this side. Okay, where you note that along the top fibers of the beam we have this kind of a tensile uh, nature of the stress, and on the bottom fibers of the beam we have this kind of compressive stresses. So this is very much under pure bending. Okay, and it is this kind of a situation which is modeled by this special case. Okay, so uh, So your next intuition would be that we should be going to the fourth degree term, and that is something we can very much do. But before we can discuss anything related to that, you please note that uh, whenever we were taking in the previous page the second degree term, and on this page this third degree term, we did not have to find any special condition regarding the satisfaction of the biharmonic equation. So if you took this form of phi and just plugged it back into the biharmonic equation, you will find that it is identically satisfied. Okay, it is actually a 0 equal to 0 form. That is because in none of the terms you have any of the you don't have any terms which are higher than 3, because these are cubic terms. So also in the previous page when we considered the second degree terms, all of them are only up to degree 2. So when you substitute in the biharmonic equation which is up to fourth order derivatives, uh, you have basically a 0 equal to 0 form, so it satisfies identically. However, if you take a fourth degree term or a fifth degree term, then you will have to find special conditions, okay, to satisfy this, and that is what is so we can write that down. So terms with m plus n less than equal to 3, uh, identically satisfy the biharmonic equation. For m plus n greater than 3, special conditions involving the coefficients various coefficients will have to be found. All right. So you can actually go forth and try the 4-degree terms. Let us not get into that in this recorded lecture. It's just algebra. Now, the basic preliminaries regarding the satisfaction of these, regarding the use of this polynomial functions uh, or polynomial forms for this area stress function that we have discussed here. But this is just like the, like, as I mentioned, very basic preliminaries. Okay. Uh, so if we want to apply this to actual problems, we have to start thinking about the boundary conditions which must be satisfied. Okay, now it will not always be so neat and clean as this. Okay, so where we have maybe some kind of a pure tension or a pure compression, in which case the values of these various coefficients can be found out in an easy manner. Okay, or perhaps it will not be as simple as this kind of simple bending also. Okay, so for more complicated problems, we have to start thinking about cleverly uh, trying to adjust the various coefficients and take various combinations. Okay, so for that we'll have to follow some kind of underlying principle, and that we'll discuss in the next part of the lecture. We'll also have to take something else into account if we think a little bit carefully. Okay, so that also will be discussed in the next part of the lecture. All right. uh, Thank you very much.